Hey guys, in this video I want to present Karamata's inequality for convex functions applied to majorizing sequences of real numbers. So first of all, let me introduce to you the concept of a vector x in Rn majorizing y in Rn. Without looking at this definition, you should think of this as saying that the largest entry of x is at least as large as the largest entry of y. The two largest ones in x have at least the sum of the two largest ones in y, and so on. And the entries in x have the same element sum as the entries in y. This is almost what our definition is saying here, but to make our life a little bit easier notation-wise, we assume first of all that the entries of x and y are both ordered in decreasing order, and then our assumption just becomes that for any k between 1 and n, the sum of I going from 1 to k of xi is at least as large as the sum of I going from 1 to k of yi. And finally, we still assume that the sum of all xi equals the sum of yi. Karamata's inequality tells us that if these assumptions are satisfied, then for any convex function f from R to R, we have that f of x1 plus ... plus f of xn is greater than or equal to the sum f of y1 plus all the way up to plus f of yn. Let me first tell you why you should care about Karamata's inequality. And for this sake, let's take a look at my favorite convex function. And note that the most important inequality we have for convex function is Jensen's inequality, which tells us that if we take 2 points here, say x2, x1, and then take a look at a weighted mean of those arguments, then the weighted mean of the corresponding function values will be at least as large as the function value at the point here. Looking at this picture, we could ask what happens if instead of moving x1 and x2 all the way to one single point, we would just move them slightly closer towards each other. We see that moving x1 and x2 towards each other at the same speed directly gives us a sequence that is majorized by x. You can try to convince yourself that using n variables instead of 2, we can also implement a weighted version of this idea. This is why Karamata's majorization inequality tells us something about the function values at y1 and y2. In this setting, we can interpret both y1 and y2 as weighted means of the xi with different weights, of course. And in this way, we can try to develop a proof for Karamata's inequality. Instead of taking this usual problem-solving approach today, I instead want to present a very complete characterization of majorization, which in turn directly implies Karamata's inequality. So while this is not the most streamlined approach, I'm excited to present to you these 3 topics in today's video. First, I will introduce permutation matrices and doubly stochastic matrices, which are just convex combinations of permutation matrices. Then we will see a characterization of majorization using doubly stochastic matrices, from which we can then finally conclude the proof. We say that a square matrix Q with 0, 1 entries only is a permutation matrix if in every row and every column of Q there's precisely a single 1. So you can think of this, if you associate the ones with rooks, as a chessboard containing n rooks that do not attack each other. A third way to think about this property is that every row and every column sums to 1. So if we fix a row I, then the sum of j going from 1 to n of the entry of q at I, j equals 1, and similarly for all j, the sum over I of qij is equal to 1 as well. Permutation matrices permute the entries of vectors under multiplication, and hence the name. For example, the matrix 1, 0, 0, 0, 0, 1, 0, 1, 0 is a permutation matrix, and multiplied by 3, 1, 5, we obtain 3, 5, 1. If we consider the arithmetic mean q plus r divided by 2 of 2 permutation matrices, q and r, then it will also satisfy these 2 properties. More generally, any convex combination of permutation matrices satisfies these equalities, now with entries in the interval from 0 to 1. We call square matrices Q whose entries lie in the interval from 0 to 1, with row and column sums equal to 1, doubly stochastic matrices. The first question you might now ask yourself is whether every doubly stochastic matrix can be represented as a convex combination of permutation matrices. This is indeed the case, and I now want to prove this fact. The key idea is that all we really need is to find a single permutation matrix that we can fit into Q. Let me explain what I mean by that by first drawing a picture of Q, where the non-zero entries are denoted by a star. If we suppose the claim were true and look at a representation of Q written as a convex combination of permutation matrices, then we could just pick one of those permutation matrices with a positive coefficient and look at its 1 entries, and then Q is going to have non-zero entries there as well. So if there's any hope to prove our claim, we always have to be able to find such star entries that form a permutation matrix. On the other hand, suppose that we can always find such a permutation matrix P as in this diagram. Then take lambda in 0, 1 maximal such that Q is greater than or equal to lambda P. So lambda will be the smallest of our red stars here, and in particular, lambda is greater than 0. Now there are two cases. First, if lambda is equal to 1, then we have by Q greater than or equal to P that Q must be equal to P, and we are already done. In the other case, it turns out that we can also find a convex combination of permutation matrices where the coefficient in front of P is precisely lambda by using induction. Namely, we define Q prime as the matrix Q minus lambda P. This now has non-negative entries and row and column sums equal to 1 minus lambda. And therefore, after dividing by 1 minus lambda, we again obtain a doubly stochastic matrix. Now Q prime has at least one more zero than Q, namely the red star that was equal to lambda in the matrix Q. Therefore, we can repeat this process and will terminate after at most, say, n squared permutations, and we can convince ourselves that this will give us a convex combination of permutation matrices equal to Q. So it remains to show that we can always match the rows to the columns in such a way that the matched entries are always positive. Thinking about this as a bipartite graph between rows and columns of our matrix, where a row and column are connected if the corresponding entry is positive, we are literally asked to find a perfect matching in this graph. Fortunately, we know exactly when this can be achieved by Hall's theorem. Namely, we need that for any subset of our rows, say I subset of 1 to n, the number of columns this subset would be connected to in our graph exceeds the size of I. So let me write down that we need that I is less than or equal to the size of n of I, which is just my notation for the set of all j in 1 to n, such that Qij is positive for some I in I. Although I'm going fairly quickly here, I want to mention that you can read up on Hall's theorem in our wiki, where you can also find all other proofs in this video. To prove this inequality, we want to look at the sum of rows I and I. Since every row I has sum equal to 1, this total is equal to the size of I. On the other hand, by the way we defined ni, it suffices to sum over j in n of I in this expression here. Swapping the order of summation and summing over all rows now gives us the bound that this is at most the sum over entries of elements in the rows n of I, which is equal to the size of n of I. So to recap, by this inequality we obtain from Hall's theorem that we can find a permutation matrix P such that every entry where this is 1 is positive in Q. Then we can subtract P with a factor that is as large as possible from Q and proceed by induction to prove our fact. Finally, there's one more thing I want to note about these matrices. Namely, if we take a look at permutation matrices Q and R, let me just write Q and R P, Then we also have that the product QR is a permutation matrix, which is not difficult to see. Moreover, I claim that the same is true for doubly stochastic matrices. Instead of doing a computation, we can now immediately see this because Q and R, if they are doubly stochastic, can be written as convex combinations of permutation matrices, and so expanding the product, the same is true for Q times R. Now let's make the connection between doubly stochastic matrices and majorization. The intuition behind this connection is that if X majorizes Y, then we can actually show that Y is a convex combination of permutations of X. But since I decided to go this fancy route through our matrices, we can restate this in the following way. Consider two vectors, X and Y, in Rn, and suppose for convenience that they already satisfy that their entries are ordered in decreasing order. Then I claim that X majorizes Y if and only if there exists a doubly stochastic matrix Q such that Y equals Q times X. If we have such a representation, Y equals to Q times X, then Y is indeed a convex combination of permutations of X by this fact, and therefore it is not hard to convince yourself that 2 and 3 follow, and therefore the proof of this direction is easy. Now we will assume that X majorizes Y and prove that we can find a doubly stochastic matrix Q with Y equals to Q times X. We are going to take a very iterative approach for this direction. Namely, we construct a vector Y squiggle and a matrix Q squiggle such that Y equals Q squiggle Y squiggle, and in some sense Y squiggle should be more similar to X than Y was to X. Through this property we will be able to apply induction so that we can write Y squiggle as Q prime X. Therefore Y will be equal to Q prime Q squiggle X, and we will be done. First of all, if X1 is equal to Y1, then we are fine by induction on N. In this case, we can find a doubly stochastic n-1 times n-1 matrix Q such that Y is equal to 1, 0, 0 Q times X, where this matrix has a 1 in the entry 1, 1, and otherwise the first column and first row are zeros, and then we have an n-1 times n-1 Q block here. Since Q was doubly stochastic, the same is true for this new matrix, and therefore we are good in this case. Otherwise, since X dominates Y, we must have X1 greater than Y1. To land in our first case, we wish to increase Y1, and therefore to maintain property 3, we have to decrease some other YK. And in this case, it is best to choose to decrease Yn by the same amount as we increase Y1, because in this way, property 1 is going to remain valid, which would not be the case for other YK. So define alpha to be X1 minus Y1, and then we denote Y squiggle by Y plus alpha times the unit vector with an entry 1 at the first index minus alpha En. All we need is to prove that we can write Y equals Q squiggle Y squiggle, where Q squiggle is doubly stochastic. The reason why we can find Q squiggle can be nicely seen in a diagram. In this example, I drew Y1 squiggle as a very large number and Yn squiggle to be quite small because Y squiggle was defined in this way. So maybe Y was originally looking something like this. Q squiggle is supposed to push these first and last indices to their appropriate positions. We can see that this can be achieved by taking Q squiggle to be equal to almost the identity matrix, where we have a lambda at the position 1, 1 and position nn, and to make up for it, 1 minus lambda at 1n and 1 minus lambda at n1 as well. The reason why such a Q squiggle works is because if we think about what happens if we swap the first and last coordinate in Y squiggle, then we will obtain a picture like this. Taking a convex combination of these two vectors with an appropriate weight will precisely land us where we want to end up. And Timo and I just did the math, which tells us that lambda is supposed to be equal to y1 minus yn plus alpha divided by y1 minus yn plus 2 alpha. Using the fact that a product of two doubly stochastic matrices is doubly stochastic, we therefore conclude our proof of the characterization of majorization. Now take a look back at the statement of Karamata's inequality. Since x majorizes y, there exists a doubly stochastic matrix Q such that y is equal to Q times x. It will now become apparent that Karamata's inequality was just Jensen's inequality in disguise. First of all, we can write Q as a convex combination of permutation matrices. So we can write yi as the sum of k equals 1 to m lambda k pkx evaluated at the index I. Applying f on both sides, we now definitely see that Jensen's inequality is applicable, and we obtain that this is less than or equal to the sum of k going from 1 to m lambda k f of pkx evaluated at I. Summing over I, we obtain that the right-hand side of our inequality, which is now on the left, is less than or equal to the sum of k going from 1 to n lambda k times the sum of I going from 1 to n, sorry, this was an m, of f of pkx evaluated at I. Crucially, since P is a permutation matrix, this entire sum is just our original left-hand side, and therefore we are summing here the sum over all lambda k times the left-hand side, which simply equals the sum of I going from 1 to n, f of xi, and therefore we are done.